Hello, welcome back to Math with Patrick. Today is January 5th, and we are solving the fifth problem in the Daily Epsilon calendar. And today is our first physics problem. I'll need to bring in some physics concepts today to solve this problem. And I'm going to write the equation for torque and walk through it before I start solving the problem. So here's the equation for torque, and it has to do with this r variable. This stands for the distance between the fulcrum, or that balancing or hinge point, the distance from the fulcrum to the force. And that's what this F is. The forces that we're going to find are from the forces of gravity on all of these masses. And that force is essentially pulling that mass straight down. We can assume that we're on Earth or something, and there's some gravity, and it's going towards the center of mass. So there's going to be some horizontal component that will be that distance of r. There is a force downwards, and that is from gravity. And this theta right here is the angle between the two. And so this is a 90-degree angle. The forces are acting perpendicularly to that lever arm, I think is the term. And so I should really quickly figure out what sine of 90 degrees is. Maybe you can think of a unit circle. 90 degrees would be right here. And the sine component has to do with the y coordinate of these points. And so this is at least how I remember my sine and cosine values. Sine of 90 is going to be this one right here. So if I take this r and this f and multiply it by 1, this part really isn't doing much. So I'll just take it off my formula for now. And torque is a concept that you probably experience every day. I'll do an example with like opening a door. So if we wanted to open a door, normally people push right here. And the idea is because this lever arm distance, this r, is going to be pretty big. And so that will make your torque larger. And this torque is kind of like a rotational force. And so it's pretty easy to rotate the door open when your lever arm r is fairly big. And people would kind of look at you silly if you decided to apply your pushing force here. And that's just because your r is going to be super, super small. And so you'd have to push a lot harder to get the same amount of torque to open up the door. And the last concept to go over before we start plugging in numbers is that torques can balance each other out. You might see this on like a seesaw, so basically this problem, where if you put a more massive object here, like maybe an adult on the seesaw, and you put them closer to this fulcrum, so their radius or their lever arm is shorter, you can balance them out with like a child or something with less mass, but you'd have to put the child further away. And so the small mass causes a smaller force, but it's balanced by the longer radius. So these two are both going down, and these two are also both going down, but they're kind of going in different rotational directions. I think what would be easiest for myself to do is just balance it with one equation where the torque from the first object plus the torque from the second object is going to just be equal to the torques on the other side. So this is my setup right here, where 1, 2, 3, and 4 just represent these 4 blocks on the seesaw. Now that I have my equation, it's time to start trying to fill it in with some numbers. So all of these torques are going to be the same as their lever arm times the force. And so that's what I'm going to write down first. And then an important physics concept is that force is equal to mass times acceleration. And we get the masses from the picture. Looks like there's 7, 5, 1, and x kilograms. And the gravity is going to cause the acceleration. And we don't really know what planet we're on, honestly, in this picture. So I'll just put G for now for gravity. I guess we could assume Earth, but I think all the gravities are going to cancel out. So here are the masses. Let's see, 751x, 751x. And then I'll multiply all of these with G for gravity. On Earth, it's around 9.8 meters per second squared. but I think they're all just going to cancel out, so it doesn't really matter what gravity is. And then these lever arm or radius distances are going to be a little bit tricky. We need to be careful here because it's important to measure from the center of mass of an object to determine its force. And the distance between this fulcrum and the center of mass of this object is going to be 1.5 of these tick marks. So I also don't get units in this problem, so I will not make any. Well, actually, let's just assume it's meters, but I also think that those units don't really matter. So we can just assume that each of these is 1 meter, and so the radius of the first one is, actually that's the second one, is 1.5, so I'll put a 1.5 here. The radius of the first one is going to be 2.5, so I'll put a 2.5 here. Set that equal to the right side. I see another 2.5 for object number 3. And then I see 1, 2, 3, 4.5 for that last one. Like I was saying earlier, these gravities are going to cancel. I guess I could think about it as dividing both sides by g, and that's going to cross off all of these terms. Just to kind of keep it nice and clean, I'll just think about all of these gravities canceling. And the next thing I'm going to do in the same step is I will also multiply all of these constant values together. And looks like I'll just be left with 3 different numbers and then some kind of, I guess that's just 4.5 times x, so 4.5x. So let me clean this up. 2.5 times 7, that's 14, and then half of a 7, so 17.5. This is 1.5 times 5, so it's 5 plus 2.5, so another 7.5. This is equal to 2.5 times 1, and then 4.5 times x. Let's simplify the left side first. I know that 7.5 plus 7.5 gives 15. So on the left side, I have a 25. Minus 2.5 will be 22.5. And that'll be equal to 4.5x. And then I'll divide both sides by 4.5. So x is equal to whatever 22.5 divided by 4.5 is. I guess we could double check with some multiplication, see what this is equal to. 5 times 5 is 25. And then, 4 times 5 plus 2 is a 22. And so that demonstrates through like a fact family that this fraction does reduce to just a 5. And so this x represented the mass of this object, and we have found that it is 5 kilograms. Thanks again for following along and solving this problem with me, and I'll see you in the next episode.